Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, as you know that we've started a series on networks and graphs, and today we are conducting yet another lecture in the same series. In today's lecture, we will try to understand the concept of performance evaluation. To discuss this topic, we have with us our subject expert, Professor D.K. Lobial. Professor Lobial is professor in School of Computer and System Sciences, JNU. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome, sir.
Thank you very much. Let me begin with how to evaluate the performance of computer network. Till now, we have studied various protocols and how these protocols perform and what is their behavior. That is most important to know, because until unless a network performs up to the expectation of the user, it does not make any significant sense. So, therefore, how to evaluate the performance of the network is important. So, we will not go in very detail of the mathematical concept of what the performance evaluation in general terms we talked about, which may be very useful for us, but this is a very introductory lecture where I will try to give the feeling of how the performance of a network is evaluated. So, let me start with what does performance evaluation mean now. The moment where performance evaluation of a computer network is the application of the scientific method to study the behavior of a computer network. So, how under different conditions a computer network behaves is crucial. So, that behavior has to be studied. Now, the two issues, how to study that behavior. Now, one, the workload, the moment I say workload, the input which I am giving to a network may be very high in a given scenario, it may be very low, it may be a moderate workload, and under different conditions the network will work differently. So, assume a situation, probably you have deployed a computer network which may perform very well, very good for a moderate situation where the traffic is not of very high volume and it gives a very good response time and everybody is satisfied. But over the period, as in an organization, if the number of users increases and the workload on the network or the load on the network is going to increase, because as the number of users will increase and at any given point of time, the moment I am saying at given point of time means I am talking of the peak time. That means when all the users of a network are available and they are using the internet or using the network for their own application. If that during that period we assume that the network is fully loaded, that means it is saturated, that means every user is transmitting his data. Now, probably you design your network for a moderate condition of the load, but in these extreme conditions and the peak hour when large number of users are using, then a large volume of traffic will flow on the network, and probably the network which you deployed for a moderate condition may choke or may not work at that condition. So, therefore, the performance is important, that in what condition, under different conditions, how your network performs is important. So, now what another word I use is, it is the application of scientific method to study the behavior of a computer network. The moment I say scientific method, that means while you are studying the behavior, it should be based on the logic and reason, right. If you apply logic and reason and maybe probably some logic, maybe inductive logic, deductive logic, what kind of logic you apply. So, by logic and reasoning, if you try to apply or study, then that is called scientific study. Now, the important point is, if you evaluate the performance of any system, now the question comes, what is the objective of performance evaluation? And these are general objectives which will also be applicable to a computer network. Now, one of the main aim of performance evaluation is to study the behavior of a system so that you can further improve it. Now, let me take a simple example. Now, say for example, in your LAN, in your organization, if you are using a router, the router may have a specific capacity that how many packets the router can forward from your network to the outside world in a millisecond or in a second, right. If I have bought a router, say it can only pass, say for example 1000 packets per second, and then as the users grow, probably a router may receive more than 1000 packets per second. Now, how under these conditions how my network performs? Now, if I am going to buy a new, replace this router which only provides you, this hypothetical example which provides you only allow you to forward 1000 packets per second. Now, there is a need arises, now you need to change, because this capacity is not sufficient to handle the whole traffic coming from your organization, because the number of users in the organization has increased. So, you want to replace now by a new router. Now, the question is, the moment you try to buy a new router, how will you decide that what capacity the router should have, the router which you are going to buy? Now, it cannot happen that you buy and then try. So, therefore, you must evaluate in advance that what kind of router, what capacity of router you need. So, therefore, if you try to evaluate that in your existing system which you are going to replace, if you keep on increasing the number of packets and you see what the performance is. Now, this is one, and then you take that theoretical data and through certain equations and mathematically you try to solve, if this is what my amount of data which is going on my network, if I model it mathematically and try to see this is my input. Now, the future input is now this much, that means the number of users has increased many folds, and you see now from 1000 users, now I have 10,000 users. If I have 10,000 users and if I need that every second 1000 packets has to be transmitted, and then what speed my router should have. So, if you can evaluate that mathematically, then you say, okay, this is what kind of router I need to buy. So, therefore, this is how you evaluate the performance and for further improvement of the system. Now, the new system will be improved, which will handle probably 10,000 packets per second. So, that is what I said, one objective of performance evaluation is to study the behavior of a system so that the system can be further improved. Second question may be to identify the bottlenecks in the existing system. See, the systems may be performing very well in a very normal condition, but we do not know when the system will choke when the extreme conditions occur. So, theoretically, probably we can evaluate the performance of system for different conditions and then see that at what condition, what load the system will choke, that is the extreme bottleneck conditions. And therefore, I will know what are the bottlenecks in my system, and accordingly I will use my system. And the third objective is to make a comparative analysis between two systems. When you are going to buy a system and normal conditions, you compare many things in the market. When you go to buy a product in the market, you try to compare between different products of the same kind, and then you say that which one is better depending on your evaluation criteria. So, similarly in the network, when you are buying certain equipments, switches, routers, whatever kind of, then you have to evaluate, and if you have multiple choices, then out of these choices you have to select one. So, then you compare. How do you compare? One, the specifications given by the seller is one, or the right, but that will not be sufficient. So, probably at times you would like to study the behavior, then you can also compare one. And the other objective is, at times I may have a mission critical system which I want to use, but I do not have an existing system. How do I study the behavior of a system if the system does not exist? Because I may not afford to buy a system and then make experiment on the system. It may be a huge, involving huge cost. So, therefore, I would like to theoretically study and then buy system based on my comparisons. These are certain objectives of performance evaluation, and these objectives will also be applicable to computer network. Now, looking at this, then the question comes when you are going to evaluate the performance of a computer network. Now, one of the key factors which we have to take into account is that what is the performance matrix. That means, what are the values or the variables which we are going to measure. That means, the output I am talking about, what output is going to come and which is significant for our study, and that is what we are going to measure. So, we have to decide what values you are going to measure, number one. That is what we call matrices or performance matrices. Now, second is what are the techniques that we should apply for evaluation of the performance. In normal, either we can use certain simulation models, you can use certain analytical models, or probably we may have some existing systems where we can have empirical measurement studies, that is what to measure, and choice of measurement tools, and then design of measurement experiment. Then if you have to conduct an experiment on the equipment, then how to conduct. That is, if you have an existing network and you want to make experiment on the existing network, then you have to decide that what to measure and then how will you conduct experiment on that system if you are using measurement based techniques. But if you are using other two, then we will discuss them further. Now, the moment I say metric, what is a matrix basically is a descriptor used to represent some aspect of a computer network's performance, right. That is, what is that indicator or the descriptor? Now, for any computer network, the matrix says the different indicators or the different descriptors which you are going to measure may capture the performance of a network as multiple layers. Maybe you are interested to measure certain things at physical layer, you may be interested to measure certain things at the data link layer, maybe at network layer, maybe at transport layer. So, at multi-layer in the given protocol stack, you may be willing to measure different things now. For example, you may be interested to measure the throughput given by the UDP protocol. So, that means at the transport layer level, you are interested to measure the throughput. And second is, at the network layer, you may be interested to measure that how much time, round trip time, that means both way that an IP packet takes. That means, if a system or a router sends an IP packet to another router, so how much time it takes that the IP packet goes there and the acknowledgement, if there, comes back to the sender. So, that is round trip time. So, at the IP layer, you may be interested to measure the round trip time spent by an IP packet. So, at transport layer, you may be interested to measure the throughput of UDP or the throughput of TCP. At the IP layer, you may be interested to measure the total round trip time taken by the IP packet, or at the MAC layer, you may be interested to measure the channel utilization. That means, for what period the channel has been utilized. So, at different layers, you may have different matrices. Now, therefore, if you look at the overall performance, the matrix which you measure can be either positive or it could be negative. The moment I say positive, negative, like say I may be interested to measure the good put, that is how best it performs. Second, I may be interested to measure the packet loss rate, that means at what rate the packets are being lost in the network. So, that is a kind of negative, or I may be interested to know that how many packets are delivered successfully per unit time, that is a positive one. I am more interested on the delivery rate rather than on the loss rate. If you say loss rate is a negative matrix, whereas successful rate, delivery rate is a positive matrix. So, they may be positive and negative. And at MAC layer, probably I may be interested to say that how many reattempts has been made on average to transmit a packet. So, retries means how many retransmission attempts are made to transmit the same packet on an average. If I may be interested to know that in a MAC layer, because probably I may have multiple choices of protocols at MAC layer. Now, question is whether I should use token ring, or I should use CSMA-CD, or token passing, or something else. What kind of protocol I should use? If I want to make a comparison, so I may be interested then in which protocol, or say I am using Aloha or CSMA, then which makes more tries and which gives more throughput. So, that is the kind of evaluation you can do. Now, the sum of the performance matrices for a computer network. In this table, if you look at, I have given certain categories, and then in the middle there are certain matrices, and in the units in which they are measured. One is the productivity of a network. So, the productivity of a network can be measured in terms of the throughput or the effective capacity of the network, and both of them will be measured in terms of megabits per second or gigabits per second, kilobits. So, megabits per second, that is what the unit that the productivity will be measured either in terms of throughput or effective capacity. Similarly, I may be interested to measure the responsiveness, right, that is another category. The responsiveness may be measured in terms of either the delay, that how much delay a frame at the MAC layer takes to send from one Ethernet interface to other Ethernet interface. Sorry. So, now this is one, or I may be interested to know the end-to-end delay. That means, when a TCP segment is sent by a host, how much time it takes to go to the other destination host, and it will also send acknowledgement back to the sender, and how much time the acknowledgement takes. That is also called an end-to-end delay of a packet or a segment of transport segment. Now, that means the responsiveness at the transport layer is in terms of end-to-end delay. The responsiveness in terms of at the MAC layer is a delay in terms of transmission time and plus the propagation time. And if you look at the network layer, it may be I may be interested to know that what is the queue size, that if a packet is transmitted, if the capacity of a router, the outgoing capacity of a router is lower than the incoming capacity at the router, then packets will be buffered in the queue, and they will be waiting for their own terms when they will be their terms for forwarding them. So, then there will be queue size. Now, the packets will keep on landing in the queue. So, what at a given point of time, what is the size, average size of a queue at a given point of time? That I may be interested to know, because that is also going to affect the time taken by an IP packet to go and come, that is the round trip time taken by an IP packet. So, that is another kind of responsive category, and that is the matrix is the queue size. Third is utilization. Then at the MAC layer and physical layer, I may be interested to measure that for what period a channel is used, and it may be in terms of the percentage of time the channel is busy, that is the measurement unit. So, then I may be interested that how many losses, that how many packets are lost, that is the packet loss rate at the network layer, or I may be interested that the frame loss rate, how many frames are lost per second, that is what the unit is, or loss percentage, that if I have sent 100 frames or packets out of 100, how many packets are lost. So, that is I may be interested to know the loss, or even at the physical layer I may be interested to measure the loss in the signal strength, attenuation. So, it is not in the, that will be in terms of probably dB, decibels, right, and loss in terms of power. Then there are issues related to the buffer problems, and then the buffer problem means I am measuring in terms of whether there is an overflow in the queue or not, right, and whether the buffer remains empty for a longer time, underflow and overflow, and that is I may be interested to measure in terms of packet drops. If the overflow is there, the packets are dropped, that will say that the buffer is overflowing. Rebuffer event, therefore I may be, then how many packets are rebuffered again and again. So, these are some matrices which are used to measure the performance of computer network. Even if you forget about a computer network, take any system in common when you have to evaluate performance. Three matrices are very common you take to measure the performance of almost any system, and that is what I thought I must summarize it here. Now, one of the matrices to evaluate the performance of any system is the throughput, and the throughput is the number of requests served per unit time, right. So, the unit time for a system may be millisecond, it may be for another system it may be seconds, for another system it may be minutes, for another system it may be hours. If you are waiting For appointment of a doctor, it may be in terms of minutes and hours, not in terms of seconds and milliseconds. But when we are talking of the packet transfer, it may be in terms of seconds and milliseconds. Now, one of the example is that how many packets are successfully transmitted in a second or per second. That is what the throughput is. And many times a student get confused with between the throughput and other matrices. The throughput definition is very clear, number of jobs or requests served per unit time. This is the key matrix used in evaluating the performance of many of the systems. Now, the second key matrix is response time. It may have varied definitions, but it is defined as the time taken to give the first response. Some books will define this and you will read this. If you are looking at the operating system, the moment you give a command and the command is executed, first time the output is displayed on the screen or display screen, you consider that time a response time. And in a queuing system or other system, it says that when the request is sent and when the request is completed, the total time from the beginning of the request till the request is completed and closed over, that total duration can be considered as a response time. So, this was also in the previous slide. The third is the utilization, and the utilization is the fraction of time for which a resource is busy, is defined as utilization. And though that means there is a relationship between the utilization and throughput. If a system is only utilized for certain lower period of time, that means throughput, if you have a full saturated system, the throughput will be lower. So, there is a relationship, but like say for example, but utilization of a specific resource. If you are using a computer system, that you can evaluate that for how long a CPU was busy. If you run your computer system for 1 hour, it does not mean for the entire duration of 1 hour the CPU was fully busy. No, the CPU will be busy only some portion of the 1 hour time. Remaining time the system may be performing I/O operations, input output operations, reading from a disk, writing on the screen or taking a printout. These are input output operations. Similarly, in the computer network, the bandwidth utilization, how long the bandwidth is busy, that is used. In a shared system, it may be busy for a long period of time, but in a dedicated system like telephone calls, when you make a telephone call, the entire bandwidth is allocated to the two parties who have established a connection. Now, whether you speak or not speak, that is used. That means when you are not speaking, the bandwidth is free. So, that is underutilized, but at cost of something else. So, utilization refers to the busyness of a resource, like bandwidth is a resource, and there is other resource may be other things like for how much time your interface is busy, so and so forth. So, these are three very common matrices which will be used in all systems. Now, we talked about three evaluation methods. One of the technique we said is a simulation model of performance evaluation. Then what is a simulation? It attempts to reproduce the behavior of a network, right, and that means in a computer network or in any system, if you want to mimic the behavior of a system, then that is what the simulation means. But how do we do that? Simulation means we try to write the program that behave like a system. That means we will write programs and these programs will try to mimic the behavior of a system which is under study, and that is what simulation means. And then this simulation represents the states of a system that using certain data structures will use, and it will use certain processes, certain events, and the event will change with the time, and that means the system will keep on changing states. If you are able to represent that through programming and write programs in different language and establish that, and then try to measure some output depending on some input parameters. That means the input parameters are the values which affect the system output, right? We call that parameters, and then the parameter is affecting the behavior of a system. We will keep on changing the parameter values and then we will measure the output. And this simulation runs when you run a program, and then you try to collect the data and analyze it at the end. That is how the system is behaving if you keep on changing the input and what kind of output I am getting. If you do that, and then probably we can evaluate the behavior of a system through simulation, through programs. But the question is, the most of the time in real life, the most of the systems are not deterministic systems, they are probabilistic systems. The moment I say deterministic systems, if I give some input to a system, if I know that what is the output of the system, that is a deterministic system. I will give an example, is a logic gate. If you use AND gate, the moment you say you give two inputs to an AND gate, you say the moment both inputs are 1, 1, you know that the output is going to be 1. And if both inputs are 0 or one of the input is 0, then you definitely know the output is going to be 0. That is a deterministic system. That means, given an input, you can determine the output. But that is not the case, general case with most of the systems in real life. That is, most of the systems in real life are not deterministic systems. That means, for a given set of inputs, we do not know what is going to be the output. Probably you know the possible outputs. Yes, of course, there are certain possible outputs. What exactly for a given at a given point of time, what exactly the output is going to be is not known. Like simple example is, if you toss a coin, you know that either head will come or tail will come, but you do not know what either head will come or tail will come at a given point of time. It may be head or it may be tail. You cannot predict whether it is going to be head or it is going to be a tail, but you know either head or tail. Possible outcomes are known, but exactly for a given input what is going to be the output is not known. That is what we call probabilistic systems, and most of the systems in real life are probabilistic systems. So, therefore, when you simulate or write programs, we must keep in mind that the most of the systems are non-deterministic systems. But it is not all the time true that we write programs. Yes, the other methods of evaluating performance is the analytical models. They are similar to simulation, but here we try to represent the system through certain mathematical equations, and we try to solve those equations. And therefore, the analytical model in computer network usually starts with the network queuing models and develop a system equation that may or may not have a closed form equation. Closed form solution means, if you take a pen and pencil, can you solve the equation or not? If you cannot solve, it may not have a closed form solution. And therefore, analytical models of computer network mostly tends to be probabilistic models. So, either we solve through simulation models or you solve through analytical models. Thank So, what we said is that the analytical models are represented a system through a set of equations, mathematical equations. They may be algebraic equations, they may be differential equations, they may be probabilistic equations, and then solving those equations to study the behavior of a system. That means, the total system's behavior is represented through set of equations, and solving them gives the performance. That is how we go about analytical model. That means one should be good enough to map a behavior of a system into mathematical equations. One. But in simulation model, one should be good enough to write computer programs for simulation. So, depending on the expertise, either you may be a good simulator or you may be a good analyst, and depends on your situation, and the expertise must be used. But these techniques have their own advantages and disadvantages, but nevertheless, before we go in details of the advantages and disadvantages, let me talk the few things about the measurement studies. Now, in addition to the simulation and analytical models, the third technique is a measurement based system. That means, when you have to study the behavior of a system, and if I have an existing system which is running and physically exists, why can't I take measurement from there? In laboratory, we make experiment and we take measurement and then analyze the system. So, that is what it is, and it involves measuring matrices from the actual systems, and the collection of data from the measurement is important, and we have to analyze that data. For example, we purposely add traffic to the network workload, add more packets, give more packets, and to facilitate the measurement, that is sending packets pair probe into the network to estimate the available bandwidth along with the flow path. That means, we keep on sending probe packets into the network so that we can evaluate, estimate what is the available bandwidth available for a given flow. That is what it is. So, you try to load, send as many packets as you can in a real system. That is what it means. Now, so we can measure the actual data and evaluate the performance. Now, looking at all three techniques, what probably might have come to your mind is the measurement is the easiest, but that is not the case. Measurement based studies has its own complications. Now, availability of a system, fine. Even if the system is available, probably in many cases you cannot make experiment with running system. Say for example, if you have a network in your organization, you cannot afford to play with the existing network. If you do it, even a small mistake may stop network for the whole day to work, and people will be annoyed with that. So, you cannot play with that, number one. And then establishing a separate systems for experimental setup is also costly. So, therefore, the cost is also involved. Time process, sometimes measurement based techniques take the longest time. See, it is not only about the computer network. I will give an example, say for example, even in the network case, the example, if you are looking at the performance of a wireless system, the signal strength you are measuring in a given location, the signal strength may depend on the various environmental factors in that location. For example, vegetation. If you try to measure the signal strength in a dry season summer, probably there is no vegetation, you find a very good high level of signal strength. But if you do it in the rainy season when the vegetation had grown high, probably the signal strength may be different. And to measure and predict and study the actual behavior of a system, how it will behave in the extreme conditions, probably you have to wait till the rainy season comes. So, it is not only that you have a system to measure it, but it also at times is a long time taking process, and how much time you want to spend. And whereas, if you look at analytical model, if you are good in making equations, make equations solve on paper and pen, can be easily done. And so, with the simulation, maybe little more time taking, but better than. But the question is, will these systems really actually give the behavior of reflect the actual behavior of a system? May not be, because these are after all the models where you take a lot of assumptions, and based on that assumptions you try to capture the behavior of a system, and in real system there may be no assumptions. So, if you have already certain assumptions, it is not actually reflecting the real behavior of a system. But still, why do we do? But at least it gives some insight into the behavior of a system and makes us or enables us at least to make certain comparative study. That is why the simulation and analytical models are important. Now, this is what we talked about, all three methods. Now, let me now focus on some of the mathematical models. I will not take a detailed, very deep mathematical model, small equations, how to measure the performance of some of the network protocols. Let me take an example of the stop and wait protocol, where we are interested to measure the throughput, which is one of the matrices. We are here interested to measure the throughput of the stop and wait protocol, which is studied in the MAC layer. Now, how does this stop and wait protocol works, and that we have studied in the MAC layer? What is studied is one frame, MAC layer sends one frame, a sender sends one frame to the destination. Either the frame may be lost, may not arrive at the destination, this is one. Second is the frame arrives, but arrives with error, right? Or third is the frame arrives without error. So, when the frame arrives without error, it will simply send an acknowledgement that the frame has come without error, everything is fine. Second case, the frame has arrived with the error, it may send acknowledgement that there is an error in the frame, and if there is an error, the same frame has to be retransmitted. Third condition, as I said, is the frame is lost. So, therefore, the destination will not know about the frame, therefore, it will not send acknowledgement. And therefore, how the sender takes a decision, it will wait for the round trip time, that how much time the previous frame took to go and come and its acknowledgement, it will wait for that time, and after that it will again resend. So, in two cases, whether the frame arrives with error or the frame is lost, even the acknowledgement may be lost, in these three conditions only retransmission has to be done. Otherwise, if these three conditions does not occur, that means the frame has arrived correctly and no retransmission. Now, when it is error free, the moment I say error free case, what I am interested in, it is not being, the same frame is not being retransmitted. So, that is the error free case. Now, in error free case, that means the frames which we are sending, they are correctly arriving at the destination, and destination is sending acknowledgement. Send one frame, reach it correctly, send acknowledgement received, then send next frame correctly, then acknowledgement, then next frame, so on and so forth. That is how all frames one by one are transmitted, and there is no error. In that case, what will be the throughput or the utilization of the stop and wait protocol? What it says is, the utilization is represented by this equation, that U is equal to Tf by T small t, Tt. That is how we are saying. That means, if the total time is Tf, total time is Tt, and out of that the Tf time is used for frame transmission. Therefore, the ratio is a fraction of time for which the system is busy. That is what utilization is, the band is busy. And since we are sending only one frame at a time, so this same becomes the throughput here. Now, the Tf is the time taken to transmit a frame, and Tt is the total time engaged in transmission of a frame. Now, how this total time is computed? If you look at the equation, the total time T is frame transmission time Tf plus propagation time T prop plus time taken to receive acknowledgement TACK, plus when the frame is arriving at the destination, it will also be, some time will be consumed in processing. That means, probably you are adding the error bits, you are doing error checking, that is called processing time. Then again, when the acknowledgement comes, it will also take some propagation time. So, propagation time, transmission time, and acknowledgement time. Now, let me explain one thing here now. What is the difference between a transmission time and a propagation time? Probably that we discuss in the MAC layer as well, but here the propagation time is how much time a bit takes to travel from the sender to the destination. When the bit starts from here and it will take some time to arrive at the destination. That is called propagation time, right? And the frame transmission time is when the frame from the buffer is put on this medium. So, one bit is put, say if I say bitwise, first bit is put, then second bit is put, then third bit is put on the wire, and then it will travel from the wire one by one. So, putting this each bit on the wire, if there is a frame of size say 100 bits, how much time it takes to put these 100 bits on the wire is my transmission time, and the total time is this putting this on this plus the propagation time Tp is Tf plus Tp is for a frame, and then when ACK, then T ACK plus T prop, then some processing time, that is what the total time. So, this is the total time will be taken by a frame, and then actual time the frame should have taken is Tf, that putting the frame bit by bit on the medium. So, that ratio Tf by Tt is called utilization time. Now, so this is how it is. Now, the other case, maybe there is error in the transmission. When there is error, then what will be the utilization now? Now, that means when there is error, the same frame which has an error will be retransmitted. Now, we do not know how many times which frame will be retransmitted how many times, we do not know. Maybe the first frame is transmitted twice, and the third frame may be successfully transmitted after making 4 attempts. Some other frame may be transmitted only in 1 attempt, some frame may be transmitted in 10 attempts, we never know. So, then what we are interested is, then on an average, how many attempts a frame has taken to be transmitted successfully. That means, after how many attempts on average a frame will be retransmitted, that is the number of retransmissions. E expectation of number of retransmissions is average retransmissions. If one frame is transmitted in 2 times, in 2 retransmissions, and some frames in 4 retransmissions, some in 10, you take average of that, you can say on an average a frame is transmitted in these many attempts, that is average. So, if the NR is the average retransmission attempts, that means a single frame on average will take NR time, then the fraction of time becomes, utilization becomes Tf by NR into Tt, because Tt is the total time taken by one frame. If the same frame is retransmitted in NR attempts, so it takes NR into Tt time. That is what the total time, if the error, it will take. So, this is what the utilization with error. Now, how to compute that? Now, if you look at it, the propagation time and the ACK time, if you look at, then what do? It is U equal to Tf by, it becomes Tp. Now, if I add this, it becomes Tf plus 2 T propagation, T propagation twice, and T ACK and T processing time we consider it to be negligible. Why negligible? Because the ACK is very small in size, maybe 20-30 bytes, and it is almost will take very small time with respect to the propagation and transmission time. Therefore, we have ignored it. And so is the processing time, because the CPU runs very fast and the frame is processed very fast. So, this time is neglected. So, T ACK and T processing is dropped. So, what is remaining is Tf plus twice of T prop. Now, the moment we say this, then the utilization becomes Tf divided by Tf plus twice of T prop. And if you divide the numerator and denominator by Tf, it becomes 1 divided by 1 plus 2a. That is what the utilization of stop and protocol with no error case, right. This is what this. So, this is one equation through which you can measure the performance of stop and wait protocol in terms of utilization. Now, what is this NR value? How do you compute that, how many attempts it will make to transmit a frame? And if you look at this, what is say is the expected number of retransmission, that is average number, weighted average. And if you look at this equation, what is said is NR is equal to summation I equal to 1 to infinity I PR of I transmissions, that is probability of I may be 1, 2, 3, 2 transmissions, 1 transmission, 3 transmissions, because some, as I said, some frame may be sent only in 1 transmission, some may be after 2 attempts 2 transmissions, some may be after 3 transmissions 3 attempts 3 transmissions. So, that is the number of transmissions for each frame may be different depending on the channel condition. So, now what is that there is a probability of transmitting a frame in first attempt, there is a probability of transmitting a frame in 2 attempts, there is a probability of transmitting a frame in 3 attempts, in 4 attempts, probability in 4 attempts, probability in 5, 6, 7 up to infinity. So, that is what the probability of. So, now the expectation is computed at IPI, that is I into if the one frame is transmitted in 1 attempt, so 1 into probability of in 1 attempt, and some frames 2 frames are transmitted in say 2 attempts, so 2 into this. So, that is what summation I equal to 1 to infinity I into probability of I transmissions. And if you solve this, what is PR? And if you look at PR, if let P be the probability that a bit is in error, if there is a bit is in error, that means there is an error in the bit, its probability is P, then the bit will arrive with an error is with probability P, and if there is no error in the bit, it will arrive without error, that is 1 minus P. Because either their bit can have an error or it cannot have an error. There is no third case, only 2 cases. If the probability of error is P, the probability with no error is 1 minus P. So, that means if you look at this small p, I said the probability that a bit is in error, let f be the number of bits in a frame. If there are number of a frame consists of f bits, then what will happen? 1 minus p is that the frame, that the bit has no error. The first bit has no error, its probability is 1 minus p. Second bit has no error, its probability is 1 minus p. And third bit has no error, 1 minus p. If there are f bits, and if out of all f bits, if all f bits has no error, that is 1 minus p into 1 minus p into 1 minus p, it is f times. That means 1 minus p or raised to the power f is that none of the bits in the frame has an error. If none of the bits in the frame has an error, that means frame has no error. That means it is the probability that frame has no error. And if you reduce, if you subtract it from 1, that is 1 into 1 minus p raised to 1 minus p raised to power f, that gives that the frame has an error, that is the probability of a frame in error is capital P, right. So, that is how we can represent it. If you look at this equation now, we say NR equal to summation I equal to 1 to infinity IPR, then what you say is that the probability of ith a frame has an error and it takes I attempts, that is p raised to power I minus 1 into 1 minus p, because in 1 minus p is that it will not, a bit will not have a frame will not have an error, capital P, and p is it will have an error. That means in I minus 1 attempt the frame has an error. So, it is p raised to power capital P is the error of a frame. So, p into p into p into p, that means if there are 11th time the frame goes correctly, that means 10 times it was transmitted with error, first attempt error, second attempt error, third attempt error, 10 attempt error, that means p capital P into capital P into capital P, that means 10 times p raised to power 10, and 11th time it succeeded, that means 1 minus p is the capital P is the frame transmitted successfully, then multiply by that. So, that is what it says, I into p raised capital P raised to the power I minus 1 into 1 minus capital P, that is a summation from I equal to 1 to infinity. Then that becomes a geometric series, and if you solve it, the answer is 1 minus 1 upon p. So, NR equal to 1 upon 1 minus p, and if you take u was 1 divided by 1 plus 2a. If you look for a without error, and if it goes with error, it was Tf divided by Nr into Tt, that is 1 divided by Nr into 1 plus 2a. Then if you substitute the value of Nr, which is 1 upon 1 minus p, this 1 minus p will go on the numerator, then u becomes 1 minus p, capital P, divided by 1 plus 2a. That is what, if the stop and wait protocol is used and the frame is transmitted with error, then the utilization has decreased now, because 1 minus p is less than 1. In case of without error, it was 1 divided by 1 plus 2a. Now, in the numerator it has become 1 minus p, p will have some value. 1 minus p will always be smaller than 1, and therefore, the value of the numerator in case of stop wait with error is smaller than the numerator of the case of stop and wait without error. So, therefore, the u will be smaller in case of stop and wait with error. That is how the performance in terms of utilization of the channel for stop and wait can be evaluated and how it will perform. Now, let me take another example of a Aloha protocol which we studied there and how its performance can be evaluated. And that is, all these are found in the normal textbook. Now, in the Aloha, what do we do? When a station has data to transmit, it does not wait, it straightway captures the channel, stands on the channel. And if more than one station simultaneously access the channel, and it is guaranteed that there will be a collision. And when there is a collision and there will be error in the packet, and you have to make a re-attempt to transmit the same frame again. Now, so that means one of the assumptions in Aloha is that the population of the user is infinite. That means any number of stations can be plugged into the channel and they can transmit. And second is, another assumption is the new frames are generated according to the Poisson distribution with the mean packet rate of s packets per given time, s packets per unit time. If unit time say 1 second, so in 1 second s packets are being generated and sent using Poisson distribution. So, therefore, the probability that k packets are generated during the given period, each probability of k is equal to s raised to the power k into e raised to the power minus s divided by factorial k. That is why the Poisson distribution is. Now, that is the probability of k packets being generated during a given period is given by s raised to the power k if s is the mean average number of packets generated during that period. The average is given by s, but now I am interested in number k. K may be more than s, it may be less than s. Then this is how it is represented. Now, looking at this, now that is, if the s may be greater than 1, that means if s is greater than 1, that packets are generated at the higher rate than the channel can handle. And therefore, what you say is the s must be between 0 and 1. It cannot exceed 1, it cannot be smaller than s. That is, average number of packets which can generate it can be not more than 1 and less. That 1 does not mean 1 packet, the 1 means the maximum ceiling in terms of normalized factor. So, if the channel can handle all packets, that means all average s packets which are generated, if the channel can send all s packets, its throughput is s. And if it can send less than that, its throughput will decrease. It cannot send more than s because you are only generating on average s. So, in addition to the new packets, the station also generates retransmission of packet that previously suffered collision. So, there are new packets arriving as well as the previous packets which failed to be transmitted are also put back in the queue and making another attempt, that is waiting for retransmission. So, therefore, the total number of packets at a given point of time is the new plus the retransmission, the packet waiting for retransmission. So, that is also we assume, it is assumed that also follow a Poisson distribution in mean g, that is g packets per time, whatever unit of time you take, that is probability of k is equal to g raised to power k into e raised to power minus g by factorial k. Now, here g is the average, the mean number of packets generated, and that mean is of both new and the old which are waiting for retransmission. So, therefore, now it is clearly that the g can be greater than or equal to s, because it includes both new and old. At the low load, when the load is low, then we will not have many packets waiting for retransmission, therefore, g will be almost equal to s, same. If the load is high, there are more collisions taking place, then there will be new plus old packets, the g will be greater than s. So, under all loads, s is equal to g into p0, where p0 is the probability that a packet does not suffer a collision. If a packet does not suffer a collision, that means it will straightway go, there is no error, no retransmission, and then how many packets we are going to send. And this is what the condition is. Now, if you look at a Aloha protocol, what do you find is, when we are sending a packet with the blue one, it can collide with the frame which was previously sent at time t0, because this frame with blue one is being transmitted at t0 plus t. So, the frame which was being transmitted at t0 can collide with this, or it may collide with the frame which will be transmitted at t0 plus 2t. So, the total vulnerable period becomes 2t, and now during that 2t is called is a vulnerable period. Then if any activity happens or any other station also transmits, then there is a collision. So, therefore, what we assume is, what is the probability that no packet is generated during the vulnerable period? Only one station is sending, no other station is generating packet, that will be P0 is equal to e raised to power minus 2g, that is k equal to 0 if you put there in the equation, then it becomes g raised to power minus k per k, k is 0, that it becomes 1, and then e raised to power minus g 2g, then it becomes P0 becomes e raised to power minus 2g, and if you put in the substitute in the equation s equal to g into P0, then we get s equal to g into e raised to power 2g. Now, if you look at this total equation, and what we are going to get is that the throughput of Aloha protocol is 0.184, that is 18%. It is a very low throughput, and the maximum throughput what Aloha protocol can give is 18%. But if you use slotted Aloha, which we discussed, then it becomes half. That probability is, the vulnerable period becomes half, that is, it will not collide with the previous one and the next one. If two packets at the same time are transmitted frame, then only collision will take place. Therefore, the throughput becomes double, that is 36%. Now, that means what we did is, through the equations, either we try to measure the throughput of the Aloha protocol, the utilization of the stop and wait protocol, and then make that in what condition how one protocol performs. That is where the performance evaluation becomes a very significant factor in measuring the performance of a computer network system. Thank you.
Dear friends, on that note, we would like to thank Professor Lobial for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.